So where did you stop? So did we talk about Saharoff condition last time, right?
Yes.
But we didn't talk about equilibrium conditions. Okay, so now Saharoff conditions. Now, yeah, we will see how Saharoff conditions work in this leptogenesis scenario. Okay, so through the right-hand neutron decay, we produce lepton asymmetry. Then this asymmetry convert to baryon asymmetry because of this Schiff-Halleran process violating B plus L. So L goes to B. In the whole process. So roughly speaking, you know, this if we inject some L asymmetry, it contains B minus L part and B plus L part. So B plus L will go away through this Schiff-Halleran equilibration. Then again, so we have to determine how much component of initial B plus L goes away. So then at the end,
So that's equal to P minus.
oh yes, thank you. So the standard model B minus L is preserved, right? So this part will remain, and then this part will be erased by some amount. Then finally, we will be determining that. Then at the end of the day, we will have non-trivial B, non-vanishing B, non-vanishing L, and then or non-vanishing B plus L, B minus L. So this whole process will be determined by chemical equilibration condition. So let's see how it works. So last time, so asymmetry of some particle, the asymmetric number density is given by determined by this so-called chemical potential quantity. So for fermion, it's just this number. For boson, we have to multiply by 2, right? Now, so right-hand neutron decays, and then when it decays, it injects lepton asymmetry in the thermal soup, and then there are Yukawa standard model Yukawa interactions, so which I write like this. And Schiff-Halleran processes. So now, so we just assume that all these Yukawa interactions, you know, there are 3 generation Yukawa interactions. For simplicity, I will assume that all the 3 generation Yukawa coupling interactions are fully in thermal equilibrium. So right-hand neutron decay to lepton and Higgs. So we are talking about, you know, the dynamics before electroweak symmetry breaking. So leptons are massless, Higgs, yeah, maybe massive. Yeah, we have 4 Higgs components, but they are massive. But their masses we neglect. So we are talking about heavy right-hand neutrinos and high temperature. And then effectively, I mean, we can assume that right-hand the Higgs is also massless. So they are in equilibrium. So we have the decay process of right-hand neutrino. But these Yukawa interactions are much faster, so they make all these leptons and Higgs are in equilibrium. So again, we assume chemical equilibrium of these particles. So we require, for the light particles, So Spaleron X in the left hand. Okay, so then for each, okay, so we define chemical potential. So let's take the notation for a left-handed doublet. I call it mu q, and for right-handed guy, I call it say u bar and d bar. So okay, so basically we can say q. Okay, so this is basically negative of ur chemical potential. But somehow I like this notation for some reason. We have 1, 2, 3, 4, 5, 6 chemical potentials. And then Spaleron X, it violates P plus L. So, and then it oops, X only on the left-handed guy, right? So, so it acts the 3 flavors, and then so this is P plus L, right? And I have okay, actually, so this is up and down. I mean the doublet. So factor 2 is always there. It's common to for Q and L, and then Q has 3 quarks. So it has 3. So this is P plus L quantity in the left-handed field. So I said the Spaleron is in Spaleron process in thermal equilibrium from 10 to 12 GeV down to 10 to 2 GeV. It's very active process. And then again, I also assume 3 YU interaction. Yucca interactions are also equilibrium. So following this notation, for each generation, okay, so this interaction is in equilibrium. So that means QL bar UR H bar is in equilibrium. So instead of QL bar, I write mu Q. Instead of mu UR, my notation is just opposite.
There is a symmetry in the right sector also?
Yeah.
In the right sector?
In the right hand, yeah, UR sector.
How is it coming?
Oh, we will see.
Okay.
I mean, we have to solve.
W I can imagine, but right sector, so it should appear really at the one loop, right?
And this is a 3-level process. I mean, we have this, okay, so we have,
Okay, continue.
yeah. Okay, yeah, basically, this we have this interaction. Okay, yeah, this is Raimund to talk about, say, Higgs and U. Or this can be any gauge version. Yeah, I mean, gluon coupling is largest, so we take for gluons, for quarks, and for leptons, W, G. They are massless anyway, so any vector version. So yeah, they are in equilibrium. So this, if we have asymmetry in Q and QL or UR, so we have to determine this quantity. So it's clear?
No, the point is that you don't have CP violation in the right sector. In principle, right? So how do you get?
Okay, we inject electron asymmetry in the soup. So this is source.
It's not dynamically generated through some.
No, it's not directly. I mean, then there are equilibrium processes. Spaleron, Yukawas, and so on and so forth, right? So then they will, this injected electron asymmetry will be redistributed by these equilibrium conditions. That's how we will be able to get non-vanishing asymmetry for each quarks and leptons. Left-handed quark, right-handed quark. Yeah. Yeah. So this is the point. Yeah, in fact, there is also flavor dependence. Yuka couplings are, quark Yuka couplings order 1, electron Yuka couplings 10 to minus 6 or sub 5. So depending on the size, some may be in equilibrium, some may be not. But things can get complicated if we include this. This is called the flavor leptogenesis or temperature dependence. But I will assume that all three Yuka couplings are in equilibrium. Then actually, so this index I becomes meaningless. So for each 1, 2, 3, they have same chemical potential, so easy to solve. So indeed, yeah. And then we have to put another condition, which is charge neutrality. So even if we generate asymmetries in each quarks and leptons and Higgses, but we shouldn't have the total asymmetry in electromagnetic charge, right? So our universe don't have any asymmetry. It should be neutral. So then, okay, then this is equivalent to require neutrality in hypercharge. And then, this hypercharge Q is Y plus T3. T3 up and down, same quantity cancels out. So this is it's a bit more complicated. So for Q, it's a charge, a hypercharge 1/6. Yes.
So the Q is the charge of the baryons.
Q.
Charge of baryons and the leptons.
Yeah, Q is the charge of each quarks and leptons.
And this delta Ni is.
It's asymmetry. So it's a mu. Okay.
Asymmetry both are.
For each these quantities.
For both the leptons.
Yeah. Okay. So this is the chemical potential of each species I. This is electromagnetic charge of each species. So if there is such an amount of asymmetry, then you have to multiply the charge of each species. Then it will give you charge asymmetry, electromagnetic charge asymmetry. And then, okay, each may have some different non-vanishing value, but summing all of them should vanish, right? And then, yeah, this is hypercharge. It has hypercharge 1/6, and three quark, 3 color, and then this doublet. So it has a 2. And then, okay, so I have, okay, so remember, this is just 1. So you just write 1, and then 2 mu u bar plus mu d bar u l I mu d bar I. And so again, this hypercharge of U bar is minus 2/3, and then we have 3 color degrees. So then, okay, I pick up minus 2, and then this has a hypercharge 1/3 3 color, and this is lepton. Doublet has hypercharge minus 1/2, and there are up and down 2 components. So this is hypercharge 1, and then just 1 component. And then Higgs has hypercharge 1/2. I mean, from this definition of the coupling. Oh, this is this quantity. Okay, so mu. So yeah, I mean, if I asymmetry of lepton doublet quark, then I have to get charge asymmetry due to this asymmetric distribution of the quark. I have to multiply the hypercharge of this guy. So this has hypercharge 1/6. Then I have to also include the degrees of freedom they have. So 3 color degrees and up and down doublet. So that's why I have 1 here. Okay. Good. And then, so it has boson has 2 degrees, and then it's has also up and down 2 degrees. So yeah, that's how we get this charge neutrality condition. Yes, and then we have all the requirement. So 5 conditions. So superleron processes in equilibrium, so it erases out P plus L current charge, P plus L charge in the left-handed sector. And then 3 Yukawas are in equilibrium, and then charge neutrality. So 5 conditions. So we start with the 6 chemical potentials, and then there are 5 conditions to be satisfied. So 1 is free, which is the source term in our case, lepton asymmetry, produced from right-hand neutral decay. So we'll take a mu L as a free parameter, input parameter. So it should be sourced by right-hand neutral decay. Now, so you can solve it, right? So then for each generation, Q1, Q2, Q3, so they are, in principle we have, this same conditions. So we assume that they have the same value. So B asymmetry should be like
Are you assuming that at least in this context, the baryon asymmetry and the lepton asymmetry are equal?
no, they can be different. Why you are thinking that baryon and lepton asymmetry should be? This is electromagnetic charge. Yeah. It has nothing to do with baryon or lepton charge.
No, I'm not talking about baryon lepton charge. I'm talking about electromagnetic charge. I'm talking about the baryon.
Baryon number is this one. Yeah. Okay. So yeah, I mean they have different. Okay. So this is this is say okay. Actually, this is electromagnetic charge quantity. This is a baryon quantity. So lepton quantity is this. Let me see. So yeah, for each quark, I mean, their baryon number is 1/3, 3 color, and doublet 2 degrees. So this is baryon number in each quark Q. And then this is baryon number -1/2. and then it's a singlet, so no factor 2. So this is this whole amount is a baryon number in d quark, and then also u quark, right? So this is if we have asymmetries in quark, u bar, the q, u bar, and d bar. So this combination will give us the baryon asymmetry of the soup. And then again, I mean, this is charge asymmetry in the soup, which should be 0. And this is lepton asymmetry. So it has a lepton number 1, this has -1, 2 doublet. So, right? Okay.
Color, you put the C3.
Yeah. Yeah, I mean, I haven't done this, I mean, a long time back, several times, and I did it again. Then whenever I do it, I have to, you know, be confused about the 30 minutes and then get the number. Anyway, but if you know the basic idea, then okay, you can come back and try to calculate it. Okay, so now the 5 week, yeah, then you just solve it. So put in Mathematica, then you will get the answer. Okay, B. I mean, okay, I forget about, I mean, basically, there is such a prefactor. It's yeah, baryon number. I mean, we are dealing with actually number, the baryon number asymmetry and lepton number asymmetry. So forgetting about this common factor. So just write, say. So I just 3. It's NF is 3 generation. Yeah, just let me equalize. Which is nothing but B. So this is minus 20 over 7, 51 over 7. This was minus 79 over 7. And often people write B in terms of B minus L because once lepton asymmetry is generated, is put from the source, then we, since we know B minus L is conserved quantity, so so from mu L, so we generate this amount of B minus L, which will be conserved throughout the history of the universe, right? So this is then we have this famous quantity factor, which is now some of you may be familiar with this number 28 over 79. Okay, for later reference, okay, actually you can from this, okay, I assume that all 3 generations have the same chemical potential. And then, okay, so then you will determine what is mu q in terms of mu L. And so on and so forth. So for 3 generation, this quantity turned out to be 4 over 7.
right-handed neutrinos at MeV scale.
Hmm?
Right-handed neutrinos at a MeV scale. You also have right-handed neutrino asymmetry.
Yes. And maybe scale, yeah, then, okay, so you are thinking of a situation where we have heavy right-hand neutrons decaying, produce lepton symmetry, or
Saying right-handed neutrons, but they have right-handed lepton number.
okay, so
So below yeah. So Dirac case, that's what
Dirac case.
yes.
You coupling 10 to minus 12 for Dirac, right?
Right.
So they will not be in thermal equilibrium. Yeah. Until T. Okay, that's a good point. I mean, gamma is, let's roughly calculate this. Okay, so yeah, typically, roughly speaking, this is interaction rate. So let's check whether this can be in equilibrium. If this is larger than Hubble expansion, then this interaction is in equilibrium. So actually, I was going to talk about this for different Yukawa couplings. Okay, basically, I mean, we have to solve Boltzmann equation and to get precise number. But I mean, for us, it's enough to see do this.
So this B minus, there is an asymmetry there because it depends on this free parameter mu or the mu. So the asymmetry is there.
Okay.
So and B plus A, won't that also have dependence on mu? The free parameter?
Yeah, I mean, yeah, mu L is the source term. Yeah, everything can be written in terms of mu L.
So why the asymmetry is there in B minus A but not in B plus A? Can it be
B plus also there is a symmetry. Okay, so I didn't write it, but you just add these two. Then you will get non-vanishing B plus L as well. It doesn't completely erase out.
But here you are assuming that initial asymmetry is coming from the leptons.
Yeah.
That's an assumption.
Yeah, that's right.
It
Yeah.
may not be true, but it's an assumption. Simplified assumption.
Yeah, this is simply observation. Yeah, that's right, exactly. So yeah, we are separating two situations. I mean, right-hand neutron decay is it's a rather slow process. There should be some out of equilibrium. If also they are in equilibrium, then we don't get this. So I just assume that there is an out of equilibrium of this process, injecting lepton symmetry from the right-hand neutron decay. So how much we'll now solve for Boltzmann equation after this. Then okay, before doing that, what I did is that then there must be Boltzmann equations of quarks and leptons involving all the Yukawas and gauge interactions. So then what I'm imagining is that, this Yukawa coupling gauge interactions are much faster, it's much larger interaction. So as soon as right-hand neutron decays, inject the lepton symmetry, and then this standard model interaction, including spiral interaction, they will summarize this injected mu immediately. So that's why we solve these equilibrium conditions, right? So now we have to determine whether this is the true or not. Okay, so I mean, okay, let's try to calculate this. Then this means that temperature below this, the Yukawa interaction will be in thermal equilibrium. So now, okay, so this is some gauge coupling. So if I take SU2 gauge coupling, so 1/30, and then y squared is 10 to minus 26. Planck mass is 10 to 18 GeV. Then what is this number? 10 to, so it's, say take 100, and then 10 to minus 28, 10 to minus 10 GeV. So if all of them are massless and then remain in thermal soup, so temperature around 1 electron, 0.1 electron volt, which is what? Is basically after radiation matter equality time. So if they remain massless until that time, they will come in equilibrium. Okay, so yeah, negligible. But you may assume, okay, there is a, I don't know, MEB right-hand neutrino, and then maybe Yucca coupling is large. Then, yeah, then we have to consider this more seriously. Now, point is that, so for top quark, this is 1. So Y is 1, and then 10 to 18 GeV divided by 100, 10 to 16 GeV. So top quark Yucca coupling, top quarks, TL, TR, are in thermal equilibrium below 10 to 16 GeV. 10 to 16 is not quite, I mean, as far as you remember, that was 10, around, yeah, it's ballpark. So accept the order 100 uncertainty in this calculation. And the electron. So electron Yucca is the smallest in the standard model. So we know that that number is 10 to minus 6, 10 to minus 5. Let's see, if we take 10 to minus 6, it's a 10 to minus 12. So then 10 to, probably 10 to close 10 to 5. 10 to minus 12, 10 to 6, or 10 to 5 GeV. You know, at high temperature, you know, electrons are not in equilibrium. But below 10 to 5 GeV, electrons are in equilibrium. And then, yeah, depending on the Yucca coupling, top quark first come into the thermal equilibrium, then bottom, tau, charm, and so on and so forth. So what I now assumed was that I am doing this at temperature below 10 to 5 GeV. So I assume that all of them are in thermal equilibrium, all Yuccas. So this calculation is valid if right-hand neutral decay is below 10 to 5 GeV to inject asymmetry mu L, right? So then, okay, then now, usually, you know, right-hand neutrino, think about right-hand neutrino around 10 to 10 GeV. Then at that temperature, only top quark. Okay, for this, I'll for precise values, more precise values. Actually, it has been calculated so long back, and then recently there is some revived interest in spontaneous leptogenesis. So you can look at the review paper by Nardi or Sacha Davidson, or it is also reproduced in this paper. So they have a nice table. So they, so let's see, Weeks polaron will be in thermal equilibrium below 2.5 times 10 to 12 GeV. And so on and so forth. So yeah, electron Yucca, yeah, 10 to 5 GeV, 1.1, 10 to 5, muon, and so top quark, 5 times 10 to 15 GeV. Okay, so we did it right.
The point is different particles, so varying asymmetries or the electric asymmetries are introduced at different levels.
Yeah, depending on the right-hand neutral mass. Okay. Yeah. So then, yeah, so let's say, so my right-hand neutral is 10 GeV, 10 to 10 GeV. Then it will decay around the temperature around that time. So around that time, the hour of equilibrium, I mean, higher temperature, you know, this guy will be taken to be massless, so nothing happens. But when temperature drops, the right-hand neutron decay will be out of equilibrium. It injects electron symmetry. Then at that temperature, we have to redo calculation, considering all this flavor dependence. So then, yeah, that's right. If you have Suji particles, this number changes. So,
But
No, essentially Yukawa coupling is same for Suji particles as well. And then soft parameter is around 100 GeV. So I think other than Yukawa couplings, there would be no flavor dependence. Seems.
No, but they may be heavy, right?
If they are heavy, say 10 to 5 GeV, yes, then okay.
Yeah, 1 TeV is safe.
Yeah, 1 TeV maybe, I don't take it seriously. I wouldn't bother to, I don't want to make my life so complicated. But usually 10 to 5 GeV, say, right? Or PEV, Suji phosphorus people talking about. So in that case, yeah, so we have to, consider this. Yes, maybe good exercise for students. And then, okay, so the reason why, okay, let's say, so 10 to 10 GeV, let's say. Then at that temperature, tau Yukawa coupling, B Yukawa coupling, top Yukawa couplings are in equilibrium. And charm as well. So then, so in this in equilibrium condition, you have to take only, first, third generation only. Top, bottom, tau. Then you will have this only out of, for only on third generation quarks and leptons are in equilibrium. Then what happens to the other? Then they don't follow this, but they are not equilibrium. So if, then you have to separate equations. Then these particles are never in equilibrium. Their interaction is not important. So, but Schuppel-Heron's don't react to all three flavors. Also, charge neutrality must be like that. Then one has to have different equations. Then conserved quantity. You have, so in that case, electrons are not equilibrium, so electron number shouldn't be changed. So then, we have to have different equations. Then this number will change depending on the flavors. So yeah, that's then I don't. And then at the end of the day, okay, so including the temperature dependence, your result will be changed by factor of 5 and most, I guess. So. You can. If you set up whole Boltzmann equation, solve it, you will get this answer immediately, automatically. Then you will see how it decouples. So so you set up how many Boltzmann equations? I don't know. So okay, good. It's a 3, 6, 9 B plus L interactions and charge neutrality. Well, probably put by hand. And then you have either 30 Boltzmann equations to solve it, and you draw the evolution of each y number. Then you will see, indeed, there's a threshold, and at some point so yeah, that's complicated. So in this approximation, maybe we just forget about this kind. There may be smooth transition, but we just step function like change. So for this treatment, it's very naive. But if you do serious calculation, you will get I don't know, factor 3. Say, you may see some up to. I'm sure the difference maybe smaller than factor 3.
Yeah, because that's because of the Boltzmann separation.
Yeah. That's right. Yeah, that's right. Exactly. Yeah, that's right. Yeah. Okay, so.
Unless you have Yukawa couplings which are weird. You have Yukawa couplings which are inverse, or some weird Yukawa couplings or something.
Weird Yukawa coupling.
Like for example, for the right-handed neutron, you can have Dirac neutron. Mathematics can have large flavor violating Yukawa.
Yeah, that's right.
In that case, flavored leptogenesis will give you.
Yeah, there will be another complication. Yeah, actually, these couplings.
That's right. So
Yes.
in that case, it can give you a factor.
Yeah. Also, here our assumption was that okay, so we forgot about this process. We just assume that at certain temperature and decays immediately and inject lepton asymmetry. But that should be determined by solving also Boltzmann equation, as you said. And then if there's a flavor dependence, 3 by 3, oh, you can solve Boltzmann equation. Nobody did it. Yeah, in principle, everything should come out from the Boltzmann equation. But since we know how it will behave, so we just make this approximation. Okay. Now, so I think we get some idea. Now, let's try to solve Boltzmann equation in this simplified cell, right? So for the Boltzmann equation of Cox and Yukawa couplings and spirals, so we just forgot about, and then we are in thermal equilibrium. So this flavor blind calculation, I will apply whatever temperature it is. Apply to TeV right hand neutrino to 10 to 10 GeV right hand neutrino. But in principle, it should be, I mean, you should remember that this temperature dependence is there in principle. So when I write some new paper of leptogenesis, then I usually forget about this uncertainty and this flavor dependence. And then sometimes the referee, some referees are very strict about it. And you didn't talk about this well-known flavor effect. Oh my God. Then I have to spend 1 more month to include it. But some references are generous. Okay, so yeah, flavor difference you include, then you will have factor 3 difference, okay? Gauge interaction, a good question. It should be there. Gauge interaction is much stronger, actually, than Yuka. I mean, gauge couplings are order 1, say. 탑과 Yuka is order 1. 탑과 Yuka와 gauge, the SU3 gauge interaction, the gauge coupling alpha, fine structure constant of QCD is 0.1. Electromagnetic, about 1 over 100. And then electromagnetic, 1 over 30, and weak. So they are usually much stronger interaction than Yukawas, except the top core. So, yeah, you usually, I mean, they are always there. But also gauge charges, they don't have symmetry. So, yeah, we just forget about it. And then, yeah, I mean, in this argument, I mean, they are still there.
That means, as the gauge interactions are strong, that is why it's harder to drive them out of equilibrium, and that is why they are not considered.
Yeah, that's right. Yeah, you can think like that. That's right. Okay, so it takes more time than I expected. Thank you for all the good questions. All right. Now, evolution of Boltzmann equation. Okay, so we have this Lagrangian, and then right-hand neutrino decay to LH. I mean, this is a neutral guy. So it can decay both lepton and anti-lepton. And then at tree level, their branching ratio should be the same. I mean, for leptogenesis to occur, we need three. We have to have three generations. We need CP violation somewhere in the Yukawa. So, but at the moment, let's just take one generation. And then, okay, this decay will inject. Of course, if they are exactly the same, there is no symmetry generated. So, at tree level, they are the same. So the difference will appear at one loop, which we will talk about in the last lecture. Okay, so the number density of right-hand neutrino follows. So 1 and 2 are either LH or L bar H bar. No, this is 4 vector. And then the decay rate of N to LH will reduce the number of right-hand neutrino by 1 unit. And then we have this phase space, the thermal distribution function, a distribution of in equilibrium, this is either Fermi-Dirac or Bose-Einstein distribution function, but we don't know now. So we will we have to determine this quantity by solving this Boltzmann equation. And then again, so we assume that this light guys are in thermal equilibrium. So for this, we take equilibrium distribution. And then in the usual case, so we neglect this one from the right-hand side because they are usually small. So and then there can be the inverse decay at high temperature. L bar is antiparticle. Yeah, L bar is antiparticle. Yeah. So for massless guy, left hand is particle, then right hand guy is antiparticle. For Higgs, H plus, if it is H plus, that must be H minus. So the inverse decay, LH to N, produces add one right hand number, so it should be plus. Then here we have FL, FH. So again, we neglect this. Okay, for this, of course, So CP asymmetry or lepton asymmetry quantity in the right-hand neutrino decay. So we'll define asymmetry quantity like this. So I mean, given Yukawa couplings, yeah, this is a particle physics calculation. So this effect, I mean, for this determination of number of right-hand neutrinos, we will not consider that such a small deviation. Epsilon is typically small, so we'll just assume they are the same quantity. And then these are light particles in thermal equilibrium. Then Fn, so we can actually parameterize like so n is the number will be determined by solving this Boltzmann equation, and then we normalize it to equilibrium number density, and then again I take equilibrium distribution function. And then it will be the equation of unknown parameter number of right-hand neutrinos, which will eventually reduced by the decay. I mean, if decay wins inverse decay. And then FLEQ. So this is an equilibrium. So for this we take I mean, so in principle, in the full Boltzmann equation, you can take a Bose-Einstein or Fermi-Dirac distribution. Then it's almost impossible to solve it analytically. So here we take a Boltzmann approximation. So meaning that FNEQ FLEQ FHEQ. So this combination then what? So this is just sum of these two energies should be conserved, the same as FNEQ, right? So this is FNEQ.
So these are, we are considering the Boltzmann distribution for all three of them.
Yeah.
But they have different masses. So it is not that they can be considered as a Boltzmann distribution at the same time. So it can happen that at some point, some is following the Boltzmann distribution, but others are not.
In most cases, no. I mean, they are light particles. So we are talking about temperature around 10 to 10 or 10 to 5. So in principle, we should take, more precise. But, okay, so by solving it numerically, you can do it. But I mean, I never did it. I just followed what people did from the beginning. And then by doing that, probably we get more precise answer. But yeah, this is what is assumed. And then, again, at the end of the day, the difference may not be that serious. Then, this is quite a simple system to solve. So say, So factor 2. So from inverse decay, so this quantity is replaced by this one. Okay, then, okay, so you plug, okay, so this is, if I, the usual phase space vector. Okay, now the kind of standard notation here is okay. Now we define S y number and number density normalized by entropy density. So I'm gonna write this equation in terms of y. So then, so you will see. Now again, instead of time, so I use.
So you have taken that all the attributes but to the same.
Yeah.
So that there is also decay, there is also so n going to LH.
Yeah.
So LH going to n.
Yeah.
Is that realistic? I mean, I understand you are doing it and
Okay. Yeah. Actually, this is exact identity for alpha.
Oh, this does not have the phase space factor. Sorry, yes. Oh, this is sorry, I was thinking of the whole thing. The decay.
Ah. Okay.
Yes, yes.
Okay.
Sorry,
Yeah. Yeah.
Yes, yes, yes.
Yeah. I mean, anyway, I mean, there's some difference. So we'll talk about it later when we talk about asymmetry of leptons. So here, I mean, I am neglecting this epsilon is difference between these two. So anyway, this will be small number. So yeah, it doesn't play important role determining the total number of right neutrinos. Okay, so I mean this is so I will define another parameter, inverse temperature normalized by the mass. So Z is dimensionless quantity related to the time. How? So we are working in mostly radiation domination. So Hubble parameter is 1/2 time, and then so this is a useful conversion relation between time and temperature, and then dz. So then, in terms of new variable, well, let us not distinguish between L bar, and so on. And then another standard notation. Okay, you just solve it. You can do the calculation analytically. So this is the final answer. Here K is the right-hand neutral decay. Yeah, it's a zero temperature decay rate. And then H1 is just H at T equals M. So H is nothing but H1 times Z minus 2. No, H is proportional to T squared. So if I introduce this notation, then in terms of H1 and Z, we have this relation. And here gamma D. Okay, so Mathematica will give you the answer immediately. Okay, so Z square K2 is nothing but that came from this this quantity. In fact, if you and then the Bessel function K1 comes from integration of including this decay amplitude squared, and then after the integration you get K1, and then K2 factor came from basically Oh, yeah, we'll talk about it. So NEQ. So you plug in just the Boltzmann approximation quantity, then what you get is so this is and then I mean in the first lecture we took the high temperature limit and non-relativistic limit, so T, much large T and small t temperature. So then yeah, Z is M over T. So this is, you know, the non-relativistic Boltzmann distribution of number. So taking this Boltzmann approximation, actually you get this analytic equation function. Otherwise, if you take a Fermi-Dirac, then yeah, we don't get. And then yeah, this Z square K2 also came from this N and EQ, and then ZK, yeah, this came from the integration of including this decay rate. So now, if you look at this, this quantity actually, I mean, if this quantity is small, that is large, then everything can be in equilibrium. So here you can see why we compared the decay rate divided by Hubble parameter. So gamma d. Okay, so actually also K can be very small or large depending on the decay rate, size of the decay rate. Okay, so you can decouple. I mean, it can be in thermal equilibrium longer or shorter. So K is a measure of when it decouples. You know, so if you do this, I mean, we did it first lecture. Interaction stronger, it will remain in thermal equilibrium, follow Boltzmann distribution longer, and then finally, when it decouples, the number density reduces, right? So the reason why we define this K dimensions quantity is to see this kind of structure. So K large, then Yn follows equilibrium delayed. So final number then will reduce. If K very small, maybe never in thermal equilibrium, K going to 0, nothing. It's 0, right? And then K equal to 1 is kind of optimal for leptogenesis. Then it's on the verge of barely in equilibrium. And then it decays immediately at temperature. Decouples at temperature is same as the mass. If K is 100, I mean the decoupling occurs later, jet around 10 or 20. So this is, I mean this behavior we'll see later. No, gamma d is just the function. It's a fixed function.
So if the right-hand term is large, so if it's 2k gamma d, this is large, that means the distribution will be equilibrium.
Yeah, the exact quantity yeah, that's a good question. Yeah, let's come back to that question later. No, I myself was confused. No, it's okay. I got it. Huh?
Gamma d is changing with z.
Gamma d function of z. Okay, so yeah, I have a note, not to confuse. Okay, so yeah. Okay, so later. Well, now you can define the decay rate to be compared with the Hubble parameter, not H1, the whole total Hubble parameter, to determine when this interaction becomes out of equilibrium, at what temperature. Is nothing but gamma n times this gamma d. Yeah, it's obvious, already obvious. Thank you. And then Z I didn't include. It's just for normalization. So if you take I mean, this is definition. Okay, good. Yes. So, yeah. So this quantity is gamma n, gamma d, h, not h1, h over z. Okay, so what you are thinking is that if this rate, this quantity is small, I mean, yeah, the other equilibrium is large in equilibrium. Thank you very much. So this is a larger equilibrium, smaller out of equilibrium. Yeah, this is a zero temperature decay rate times this function. And z, I didn't consider it because, I mean, it can go to left-hand side, so z over dz is normalized to be 1. So this is the right quantity. And then, yeah, and the high temperature is just okay, so, yeah, also interesting to see this. So gamma d at high temperature, gamma n times z and 1. So low temperature, T going to 0, this is vacuum decay rate. High temperature is m over T. So high temperature is suppressed, rate is suppressed. Is it reasonable? Okay. And then, okay, we will come back to this, the meaning of this, significance of this quantity in terms of asymmetry generation. All right, so now, this is kind of a trivial part, and then we have to talk about asymmetry generation, which is tricky, which contains some tricky points. Okay. By the way, different references, different people use different notation. Little gamma d I define by k1 over k2, but some people define including k or whatever. So you have to be careful about it. But for some people, big gamma d is denoted by little gamma d, and so on and so forth. Evolution of that equations. Okay. So let us use this notation to denote asymmetric quantity. Okay, so we taking the Boltzmann approximation, if there is a symmetry mu, then this will be is that factor 2? No, something not here. And then mu, we don't know, so it will be determined by solving the Boltzmann equation we are going to set up. And then, okay, so then you do the integration. Then, okay, first part will give us the usual, integration, the equilibrium number density which we calculated, z square k2. And then difference, okay, factor 2 comes from the difference. Okay, this has a mu over t, this has a minus mu over t. So this factor 2 here. And then normalized by entropy density. Okay, so this will determine by solving the Boltzmann equation. So Boltzmann equation in terms of this is nothing but the Boltzmann equation in terms of this quantity, right? Right. Okay, so the previously from the inverse decay we had this quantity, right? So then this will be so for the Boltzmann equation of right-hand to decay, we just took this leading part, ignoring asymmetric contribution. So I have L and H. So the mu L, mu H, mu L will be sourced by this right-hand to decay H. We know how it was determined through thermal equilibrium condition. So I think we have to include this mu H here. And L by H bar take minus and LH take plus.
H is neutral, right?
H is complex. H plus H minus H0, H0 star. We are talking about
Unbroken phase.
unbroken phase. We are talking about temperature higher than the electroweak scale. Yeah. That's right, exactly. So in most cases, we neglect their masses. At high temperature, they have a negative mass squared. But high temperature symmetry is restored because of temperature dependent mass T squared. So then, in principle, in this calculation should include the dispersion, including temperature T squared mass. But you usually forget about it. So its effect is negligible. But not completely. In some cases, one has to take the temperature effect more seriously, but naively, we just neglect it. Actually, the
Square effect is important for, say, EV or sub-EV masses or something.
yeah, that's
For heavy masses,
yeah. Okay, so we are considering dynamics actually above electric scale, the unbroken phase, and then T squared temperature. Okay, for the Higgs, we have YT squared or alpha. So symmetry is restored. So then all the four Higgses neglecting this may have the same mass, temperature dependent mass. But this temperature dependent mass is typically smaller than the temperature itself. Not quite. I don't know, maybe that's factor 4 pi or something, So we usually neglect this effect. But in certain cases, actually the complete paper by Judith et al., they include this temperature-dependent contribution and try to solve virtualization using, temperature-dependent quantum field theory. In principle, it has to take a temperature-dependent propagator and the masses. Until 10 years ago, people really tried to do it more rigorously, and then actually my follow-up to leptogenesis stopped earlier than that, so I didn't follow this new progress. But that was done by many people. But at the end of the day, no big change. Okay, so I usually neglect. So we take them all massless, LH, whatever. Massless. Oh yeah, they must have also temperature d squared mass. Yeah, they have gauge interaction, so g squared times d squared. We neglect. Yeah, good. Okay, so Boltzmann equation. Okay, the same one. D phi 3 particles, energy momentum conservation. Oh, there must be. And then right-hand neutron decay to LH produce one lepton, so it has to be added. Then here you have Fn. Inverse decay reduce by 1 unit. Okay, so for FL, FH, we take equilibrium distribution. For Fn, as we did. Again, Fn. And now since we are, okay, for anti-lepton, we take negative sign here. And then we subtract these two. Then now we have to include the difference between include the CP symmetry. This is identity in quantum field theory due to CPT. Yes. So we quantify their difference by epsilon. Okay. What am I doing? Yeah. I mean, compared with this antiparticle decay. Then obviously this will be 1 minus epsilon. So epsilon is this CP symmetric quantity of right-hand neutron decay. Now, I mean, this must be non-vanishing. at tree level, they are the same. So there should be, the answer is that, okay, so symmetry appears only at one loop. Then there are some interesting properties to get also non-vanishing epsilon, so which we'll be talking about. We'll discuss in the last lecture. Probably I might have 2 more lectures. I don't know. Okay, so now so let us write down the asymmetry evolution. So this factor I won't write. So okay, from this I get so I have this integration, and then inside the integration I have so now, okay, so this was then, so we actually replace this by this quantity. And then first the meaning of this is what? So from there, if there was a non-zero lepton symmetry, so this will give negative contribution to the final asymmetry. So this is due to the washout of inverse decay. And then this is from decay. Fn decays to right-handed terms, then for each number of n, we get epsilon asymmetry, right? Asymmetry of amount epsilon. And then this quantity also should be of the same order of epsilon. So it's producing asymmetry, it's recovering symmetry. So there is this 2 competition, but there is a plus sign, which sounds not correct, right? So that it means that even if this right-handed is in equilibrium, they will decay, add up, which shouldn't be the case. When we talking about decay, NN, YN evolution, we had negative sign. So when it's equilibrium, it vanishes, nothing happens. So, this is one tricky point. And then another tricky point is this. This I never realized before. So when I prepared this note, I thought that there must be mu h there. And then mu h through equilibration condition we determined to be so we saw that from standard model equilibration condition mu h, there is a redistribution of total symmetry. At the end of the day, we should have this. And then that quantity is 7/11 times mu L. So this is so what I will have in this side is 2 YL EQ Y delta L FNQ times this factor. But if you look at any literature, nobody wrote this. So that was taken to be 1. So I also took it granted. But now I am, while following this calculation, oh my God, I mean.
So it is larger.
Huh?
The washout factor is larger.
Larger. But it's just 11 or 7. So now, I mean,
15%.
yeah. So please correct me. Muir is prepared. Yeah, Muir is I mean, we will determine by solving this Boltzmann equation. Right? So this is source term injecting. So when I just followed a long time ago, this calculation, okay, there is a symmetry in Y, so just to put Y delta L here. And forgot about X. Maybe I'm missing something. So, but so far I couldn't find any. So I hope one of you can confirm or disprove this. Actually, the review paper by Davidson and Nardi, they talk about that factor CLH, in my case 11/7, including all the flavor dependencies. They have a table where this CL is, I don't know, 237 divided by 121, something like this. Depending on the temperature range, when leptogenesis occurs, we have different numbers. And then they have this complicated table. And then I try to follow the calculations in more detail, but somehow not easy. But anyway, I mean, this is a simple kind of process. So maybe I missed something, or people just ignore this factor. I mean, again, 11/7. It's not as dangerous as taking Boltzmann approximation.
So here, so if Muir has a greater value, that would mean greater asymmetry.
Yeah. Larger mu L means obviously larger Y delta L. Yeah. Which one? Sorry, I didn't. This one? Yellow.
So this contributes to the negative sign?
No, this.
It's the same as the
No. I am just rewriting. Yeah, I'm just rewriting it. Yeah, minus. Yeah, minus. Yeah, no. I mean this one. Okay, so then the another tricky point. We will come back later.
because similar amount of asymmetry should be there in the fixed center also.
Yeah.
So why don't we talk about
in the beginning of the lecture, we determined the mu h through the equilibrium conditions. So what I think is that we should put this number in this equation, which may not be correct. Since I saw nobody talking about that. Okay, so this is recorded, right? Please later erase this part. Okay, so yeah, any question?
What is there any constraint on mu L from some value of
It comes from, it should be 10 to minus 10. Yeah, approximately. Yeah, YB is 10 to minus 10. So YB is proportional to Y delta L. We will be determining.
Lepton symmetry is much weakly constrained.
Lepton symmetry, lepton symmetry in the charged case should be neutral, no symmetry. But neutrino symmetry can be, I don't know, probably it's up 10 to minus 3, 4?
Yeah, 3 or 4.
Yeah, the number I remember is 10 to minus 3, kind of, which comes from?
BBN and CMB.
Yeah, BBN, okay, yeah, okay, it's larger than 10 to minus 3, it will contribute to the extra degree of freedom. Okay, yeah. So then, except that there is no constraint at all. But if you believe in this Lepton symmetry, then okay. So asymmetry in neutrino should be around 10 to minus 10 as well, right? Well, I don't know. I mean, yeah. Anyway, the direct constraint is 10 to minus 3. Okay. So actually, and then actually some people, I mean, we can play with this. So if neutrino symmetry 10 to minus 4, there appears some interesting phenomena. Okay, good. Let's stop here today.